the book on the ground. That was that I'm an analyst. Thank you for joining. I am Marcus, and I did advice to college deliveries and Ireland and overall there are the more sectors aimed at the sun. I guess I when you get to audience, there will be trucks over the world of regardless of your privacy, we are expensive. And so they still do just that's it's just so all the agreements in again like just the Dutch have it in our forwards and in this basically to wait all one people's ever sponsor about the end. We'll take while they put the call and stuff like that. In there, so consumers help and that's they just little kind of they just really was brings back the straightforward Java code while also unlocking a massive concurrency. All of this just proving that sometimes the best evolution is just a return to simplicity. This is the agenda for today's talk. We'll start with a multi-threading example in a real-life situation. Then we'll ask ourselves, how many threads can we create? Little by little, we'll move into code and see a basic example of a single-threaded application. Then we'll naturally move to executor service. Then we'll see how we can evolve, and we'll see the advantages and challenges of reactive programming. And finally, the highlight of our session, virtual threads. For the next 3 slides, let's step away a bit from the IDE and make some analogies between some high-level thread concepts and a virtual restaurant. That's because blocking, non-blocking, threads, queues, all of these are invisible. So let's warm up a bit with these analogies. So imagine this is a kitchen. Inside we have 4 grills, 4 chefs, and this small icon there means that each chef is cooking. In this analogy, the kitchen is the CPU, the grills are the cores of the system, the chefs are the threads, and the cooking is a CPU-intensive action. In this model, all our resources are consumed at 100%, so adding more chefs in this model will not bring any more value, because they will spend their time just waiting. So let's enrich a bit our models and add one more actor, a freezer. Now, each chef, when they want to cook a meal, they first need to go in front of the freezer, take out the frozen pizza from inside, and wait for it to defrost. Yeah, unfortunately, it's not a very good restaurant. They use frozen pizza, but yeah, it's good enough to run our example. So only when the pizza is defrosted, the chefs can take their place to the grills and start cooking. In the meantime, another chefs can start their waiting actions. And whenever a grill is free, because one chef finished their cook, they can directly go and start cooking. And this can happen again and again. And an obvious question could arise here. What if we add more chefs? A lot more, I mean. We managed to arrive in a point where more threads than the number of cores were helpful. Because yeah, we have 4 chefs who are actively cooking and 4 chefs who spends their time passively waiting. But it doesn't mean that we can add more chefs who are just waiting, because yeah, they don't bring any value. It's enough, this model. In case you figured out, this model mirrors almost perfectly the executor service in Java. And now let's see how virtual threads brings to our table. We have the same model, same actors, but we have a twist here, because now when a chef wants to wait for its pizza to defrost, they don't have to stay in the kitchen anymore. They just have to write a recipe and tell them something like, okay, I'm waiting for this pizza, call me when it's ready, and just leave the kitchen and make space. And other chefs could do the same again and again. And whenever the first bunch of pizzas are defrosted,
they just come back and take their places to the grill and start cooking. This model has a lot of advantages because we don't have wasted space because waiting happens outside the kitchen. We don't have wasted time because each grill is used 100% of the time. We don't have wasted money because, in this analogy, we don't want to pay our chefs while they are just waiting. It's like they are not at the job, they leave the kitchen. And also we have virtually unlimited scale because waiting happens outside the kitchen, so we can coordinate thousands or even millions of chefs without running out of space or budget. And let's ask ourselves, how many threads can we create? The easiest answer could be as many as we want because, a thread feels cheap. But in our domain, we should be as efficient as possible, not do guesswork. And let's adjust a bit the question and ask ourselves, how many threads should we create? Fortunately, we have a formula for this number of number of threads are less or equal than the number of cores divided by 1 minus blocking factor. What's this blocking factor? It's a value between 0 and 1 and represents how much time a thread spends its time waiting. So for a CPU-intensive action, the blocking factor is or tends to be 0, and for a blocking-intensive action, the blocking factor tends to be 1. So let's put these numbers into some visuals. Here we have a correlation between the number of threads and the execution time. We took 3 cases, one for a CPU-intensive action, one for a blocking action, intensive blocking action, and one for in between. And just focus here on these 3 points, each per every case. And these points represents a sweet spot where the number of threads were correctly chosen. Because adding more threads than that sweet spot means wasted resources because, as you can see, the curve flattens. So it don't gain any advantage in the execution time. So this thing has a bigger business angle here because when performance dips, the easiest reflex is to scale horizontally. To add more servers, more cores, more containers. So we, in our company, we try to place our code in the proximity of those sweet spots. And with this, we can gain a lot of efficiency in the infrastructure costs. And also, we can promote sustainability because we don't consume wasted resources. Okay, we've spent some time in the kitchen playing with some analogies, but now let's see how all of this works in real Java. Here we have a simple code, the kind of blocking code we as developers wrote more than 20 years ago. Pure sequential, 2 blocking actions executed one after another, and then when we have 2 results, we can create an object to use them. For many years, developers loved this style. Why? Because blocking code is straightforward and readable. You can read it from top to bottom, just like a story. This clarity was, and still is, to be honest, a huge comfort when writing and debugging code. But you can guess that it didn't take too long for developers to hit the limits of pure sequential execution. So the natural step forward was parallelism. And the Java's answer to that was executor service, a framework that makes it easy to spin up a pool of worker threads and run tasks side by side. So we still have blocking code here, but at least it is those 2 actions are executed in parallel on a different platform thread. What is a platform thread? Sorry. What is a platform thread? It is a thin Java wrapper around the kernel of the operating system thread. It takes about 1 megabyte to start, about roughly 2 megabytes to hold its stack, and each context switch costs us 1/10 of a millisecond. Because of this cost, the practical number of platform threads you can create at the same time is physically limited, because we can have only a few thousands of them. To be honest, this is perfectly fine for many workloads, but it becomes a real constraint when we need to handle tens or hundreds of concurrent connections. So, why is it so wrong to block a platform thread? First of all, each platform thread is expensive. Yeah. Starting one takes memory and CPU, so keeping it idle while waiting is a direct cost. Then it blocks limited physical resources, because every block thread consumes capacity that could be used elsewhere. And third, CPU time is wasted, because we aim to have the CPU as active as possible, to use it at its maximum capability. Okay, together these factors create a huge scalability ceiling, because as the number of locked threads grows, the application cannot effectively handle more load, no matter how much hardware we add. Now let's take these issues one by one and see how they manifest into code. I will not bore you too much. Have this executor service, so each background task thread blocks the main thread. This is the first issue. The second issue is that imagine if one thread crashes, the second one will keep running unlimited. That means that the second thread may keep running in background with no one waiting for it. So it basically becomes an orphaned or a loose thread. The third issue is linked to debugging, because imagine we have an exception in one of those two background tasks. This would be the stack trace. We could identify two issues here. One is that the exception is wrapped in an execution exception, so we have a new nested level to search. And also, another issue is that the stack trace doesn't point exactly to where the error occurred. It points to the get method on the main thread. So then you should Control F and search it manually. And the last issue in code is that it's wasteful and unnecessary, because imagine, why would you want to have one of the most important threads in your application, the main thread? Why would you want to spend its time just waiting for some background task? So it doesn't make too much sense. Now let's see how we fix these issues. We have two variants. Let's take them one by one. First of all, reactive programming. It lets a single platform thread handle many concurrent requests, upon around 1,000 requests per thread. This dramatically reduces the number of threads, cuts memory usage, and removes the hard scalability ceiling we've seen with traditional platform threads. By the time reactive programming arrived, developers were kind of ready for it, because it solved the pain of managing thousands of blocking threads, and the community welcomed the speed and efficiency it brought. Here you can view how we can write the same functionality as before, but using reactive programming. Again, I don't want to bore you. It's basically a project director code with a publisher, the mono, two parallel requests, then map the responses in order to create a meal plan, and we'll call the block in order to subscribe and basically execute those actions. But now let's see how that platform thread is used under the hood. Imagine this line is the timeline of a platform thread, and each dot you see will be events on that timeline. So first we call read ingredients, then somewhere in the future we'll get the response of read ingredients call, and you can see that there is a span of time in between. A project reactor just fits another call in that time, the read recipes call. In the future, we'll get a response for that call, and more in the future, we can create the meal plan. But you still see some gap in between these events. So project directors just take another clause and fit this time with other events, and the aim is to use the platform thread at its maximum capacity, 100%.
Good.
Okay, so a single thread can jiggle a lot of requests, keeping CPU busy and memory as low as possible. So it's the most efficient way. We have the highest throughput, but here is the catch, that this efficiency comes at a heavy price because the code becomes quickly complex. It becomes hard to write, how to read, how to test, and that's because asynchronous flows don't behave in a simple linear way. The pain just doesn't stop there because the reactive programming code is basically impossible to debug and profile. So yeah, asynchronous programming brought impressive efficiency, but it also brought a level of complexity and, most important, opacity that made everyday development much, much harder. So now, let's go to the second option, virtual threads, which are a much lighter model than platform threads. How much lighter? Roughly 1,000 times lighter. And now let's see how we can reach this performance. A virtual thread is managed by JVM, and it's basically attached to a platform thread, which in this context is called a carrier. And whenever a blocking action occurs, JVM just suspend and resume the virtual thread from that carrier thread. So in the time during a blocking action, the virtual thread is moved to the heap, and the platform thread remains free to take to take other jobs. So yeah, all of this make virtual threads much cheaper and lighter than platform threads. And another advantage is that you don't need to map a new mental model in order to work with virtual threads, because we can use the same method and classes we used with executor service, like start, synchronize, and so on. So yeah, it's the learning curve is steep. We have four characteristics. First of all, it's extremely fast to create. So from milliseconds to microseconds, it has a tiny memory footprint from megabytes to kilobytes. So yeah, you can see the trend, 1,000 times lighter. We have a huge scalability because they are so light. We can run hundreds of thousands or even millions of concurrent tasks on the same JVM. And finally, it has a natural blocking model because we can keep the simple sequential style of straightforward Java. Yeah, it's easy to learn them and use them as soon as possible. You know this code, it's an executor service, so the only change we should do in order to change it to use virtual threads is only one line. So from new fixed thread pool to new virtual thread per executor. This tiny change delivers a huge impact. No heavy platform threads, no complex refactor, but massive scalability and lower memory usage. This is exactly the kind of upgrade we want from JDK. We want major benefits with minimal code changes. And that's exactly we would adopt as well, because we like to make a huge improvement in our code, but also without making complex and risky refactorings and other changes. Let's see how virtual threads work under the hood. So we have a for example here with two platform threads and a heap. JVM creates a virtual threads, mount it on top of platform thread 1, which became a carrier thread in this context, start a job, and whenever it hits a blocking action, JVM simply detach the virtual thread from the platform thread and moves it to heap, leaving the platform thread 1 empty to free to take another jobs. And when the blocking action is finished, JVM simply brings back the virtual thread and mount it again on a platform thread. It could be the first one, the initial one, but if that one is busy, it can take another free platform thread. It's not a problem. Now let's continue with virtual thread states. We are all familiar with these 5 states built in green because they exist with platform threads as well. We have 3 new: parking, part, and pin. Parking and part are quite intuitive. They are because of that suspending and resuming mechanism handled by JVM. But let's stop on the pinned one because I want to be honest with you, virtual threads are not a perfect solution. So there is this case when JVM can't unmount the virtual threads from the carrier thread, and it will behave exactly like a traditional platform thread. And those cases are when we deal with native code, with libraries which haven't adopted yet virtual threads. We should do some tests in isolation first. And another case could be with blocking code in synchronized blocks. So they will behave like regular ones in those cases. Let's speak about benchmark a bit. I've created a short program which easily spins 2 thread pools of 10,000 threads. Each of them programs to sleep for 1 second. One service is with platform threads and one with virtual threads. So these are the results after I executed them. You can see that virtual threads are around roughly 5 times faster, and that's because blocking tasks scale almost linearly where we are dealing with virtual threads. And in the case of platform threads, we have needed to batch them in batch of 2,000 threads, and that's why it is 5 times faster, right? Cool. So that's the end of our story. We started with writing blocking single-threaded code. Then we naturally moved to executor service. Then we've seen the advantages and challenges of reactive programming and what it brought in our lives. And we finished with the highlight of my presentation, virtual threads. All along, our goal was to write simple, readable Java code that still scales to today's massive workload. So that's the key of my presentation. Simplicity is the ultimate superpower, because with virtual threads, we don't have to choose between clarity and scalability, because we get both of them. They fit perfectly with this philosophy. We want smarter software instead of more hardware. We want clarity instead of complexity, and value that our developers can measure not only in performance, but also in lower operating costs. So again, I was Cosmin Baciu, engineer and manager at Deloitte Technology Delivery Center. Have any questions? If not, we'll be here if you have something. You can contact me anytime you want on my email. Thank you very much for joining.